In this lecture, we are going to look at the Claisen Ester Condensation reaction. Now, if you have gone through the lecture on the aldol condensation reaction, this particular reaction wouldn't be a difficult problem to you. So, what is the Claisen Ester condensation reaction all about? Now, if I will read what I have here on my screen, say the self-condensation of an ester is referred to as the Claisen Ester condensation reaction. The labile alkoxyl group is eliminated from the alpha ketoester as the final product. Now, this may seem like Japanese to you. I will try as much as possible to explain it in the simplest term possible so that everyone will be able to comprehend what the reaction is all about. Now, in our reaction on aldol condensation reaction, if you can still remember, we said that two aldehyde molecule condenses together to form a beta hydroxyaldehyde, or if it is a ketone, two ketone molecule condenses together to form a beta, this will form a beta hydroxyaldehyde, or if it's a ketone, it forms a beta hydroxy ketone. But in this case, what we are actually condensing with itself is an ester. So you see that the process would almost be the same, but just a little variation. Now, if you look at what we have here, these two here is telling us that we have two molecules of the ester. This is an ester, of course. This is 1,2-ethyl propanoate. Okay, it's an ester. Now, when ethyl propanoate condenses with itself, it forms this, which is an alpha ketoester. Now, why did they call it alpha ketoester? Is because at the alpha position, a keto group is attached to it. Are you getting it? This is the functional group here, right? This is the what? Alpha. Then at this position, what do you have here? A keto group is attached to it. That's why we call it an alpha ketoester that will be formed. Then alcohol will be eliminated. In this case, the alcohol eliminated is ethanol. Are we getting it now? So let us look at the mechanism for this reaction. So if I will reiterate what I have here, I said that the Claisen condensation reaction is a reaction that requires two ester condensing together to form an alpha ketoester with the elimination of alcohol. So let's see a particular reaction that has to do with this and see how the product is formed. Now, in our textbook, you see something like, or in our material, something like ETO minus. This is still the same thing with what we have here. This is etoxide. This is the formula, the molecular formula of the etoxide in question. Okay, so let's see how the reaction takes place. You say a base removes a proton from an alpha carbon, creating an enolate ion. So first of all, we are going to start by writing two esters. Are we getting it? Or first of all, let's write an ester, or let's react two esters so that we know what we are talking about. So this is an ester, CH, and then you have C, double bond O, and then here is O, and then here is let's say here is R. That's what makes this an ester. Okay, plus another ester again, the same ester. So this R, CH, then we have, no, this is supposed to be R, CH, then you have C, double bond O, and then OR. Now this is an ester, and then this is an ester. Of course, they are the same ester. Are we getting it? Or to make things easier, let me just go straight to giving a specific or a named ester for the reaction. Now, if I should use a named ester, let's say something like this: CH3, C, O, and then O, CH3. Now, plus we are using the same ester, so this CH3, C, double bond O, then O, CH3. Now, the first process step 1 for the mechanism of the reaction is that a base removes a proton from an alpha carbon, creating an enolate ion. So first of all, we have to choose the one that is the alpha carbon here. Now let us pick the first ester. So if we pick the first ester, we are going to have this CH3, and then we have C double bond O, and then O CH3. Okay, now the question you need to ask yourself, in this reaction, which base was used? I told you it's a alkoxide, which is CH3 CH2O minus. That is the base that was used. So let's see how a alkoxide reacts with this to form the enolate ion. Now, first of all, you have CH3 here. Now, the question is, which of these carbon is the alpha carbon? You agree with me that this is the carbonyl carbon. Now, the carbon close to the carbonyl carbon is the alpha carbon. So in this case, this is the alpha carbon. So we have to remove a proton, which is hydrogen, from the alpha carbon. Now, to make this easier, this CH3, right? I can decide to write this as CH2 and then the hydrogen that connects it here. Now, if this hydrogen adds to this is CH3. Why? The reason why I wrote it like this is so that there will be easy abstraction of the proton. That means the proton can easily be removed, okay? So if this, which is CH, this is entanol, I can decide to write it as O minus, O negative. Then we'll have CH2, CH3. Now, entanol, we abstract a proton. Now, entanol is a good nucleophile. I would say nucleophile usually abstracts proton. Are we getting it? So if this nucleophile attacks this hydrogen here, what will happen? It will take the hydrogen from this bond. And we know that I said in the video on alkyl condensation reaction, if you do not watch that, please make sure that you go through that before coming to watch on the Claisen Ester reaction. Now, as it attacks this hydrogen, something happens. This bond here kicks into this position. Are you getting it? Because when it's abstracting a proton is H+. That's why we said it is abstracting a proton, not a hydrogen. Proton does not have an electron. So the electrons that form this bond still remains. And that is why the electrons will kick in here to form a negative charge here. So the product of this reaction would be, what do you think would be the product? It will be, you have CH2, then you have C, double bond O, and then OCH3, okay, with a negative charge here, which is the proton that the electron that kick in after the proton was extracted. So you have a negative charge here. Now, when these two add together, when this proton is being abstracted by this alkoxide ion, what do you think we form? This one will form OH, right? So this will be plus CH3 CH2, which CH3, CH2, and then OH, which is an entanol. This is one of the products of the reaction. So the first step of the reaction leads to the formation of the enolate ion. Now, which of them is the enolate ion? This is the enolate ion, okay? Enolate ion and what? Alcohol. Which in this case, the alcohol is ethanol, okay? So that is for the first case. Now, we are using two esters, or we are reacting to esters. We've used one to form the enolate ion. Now, the next step is the unionized ester react with the enolate ion, which is this other ester, the second ester, react with the enolate ion. So let's bring that out to this other slide. It says the enolate ion adds to the carbonyl carbon of a second molecule of ester. So let's write out what we are expected to have here. Now, this is the C double bond O, and then this is what? CH3, and then this is what? OCH3. This is the unionized ester. And then you have CH2, there is a negative charge here, C double bond O, and then OCH3. What do you think is this? This is the enolate ion, okay? This is the enolate ion. So what we had here was what I brought here. So this is the enolate that was formed from the first ester, and then this is the what? Unionized ester group. Now, for the reaction to be, for us to have a good reaction, let us orient this in such a way that when this is coming in, it wouldn't pose more problem or much problem. So what I'm going to do now is I'm going to quickly erase this. It's still the same thing. I'm just trying to make sure that there is no steric hindrance, okay? Erase this. It's still the same thing I'm writing. This is CH3, and then here is what? OCH3. It's still the same thing. True or false? It's true, because it was initially, I just placed it here so that when this is coming in, it wouldn't hinder it, okay? So at the end of the day, what am I expected to have? This negative charge is a good nucleophile. And we said that nucleophile actually attacks a carbonyl carbon, okay? So this nucleophile here attacks this carbonyl carbon. When it attacks this carbonyl carbon, what happens? This one here will undergo mesomeric effect, and then it will pack up here, okay? So at the end of the day, what do you think will be the product of this reaction? The product of the reaction would be something like this. We're going to have CH3, right? There you have C. Here will be what? O minus. And here is what? OCH3. Now don't forget that this one, they still have their own normal lone pair normally, okay? Then we have here, since this one has donated this electron here or this bond here, there will be a bond, a linkage between this and CH2, right? The net result of what happened here is that there is a linkage here, okay? So what I'm going to have here is something like a bond. Then we have CH2 and then C double bond O, and then sorry about that, we have CH2, C double bond O, and then OCH3. Now this is the second step. Now let us look at the third step. You say the carbon oxygen bond reform, eliminating the alkoxide ion. So what I'm going to do, I'm going to write everything that I wrote there again. So this is CH3, this is C, this is what? O minus, and this is what? OCH3, and then this is what? CH2, C CH2, then C double bond O, and what? OCH3. Now at the end of the day, what do you think we are going to form now? Or what do you think will happen? Read the step. You say the carbon oxygen bond, pi bond, reforms. That means what we are trying to say is that this bond here reforms, eliminating the alkoxide ion, which is more labile. As this one is coming in, the group that will leave here is the alkoxide ion, which is this. This ion will be eliminated, okay? So at the end of the day, what do you think we are going to have? So this one comes here to form a double bond. As this one is coming here, the valency of carbon will be more than 4. And carbon, of course, you know, it's supposed to have a valency of 4, right? This is coming here to form 1, 2, 3, 4, 5. Carbon is supposed to have a valency of 4. So if it has 5, it can't stay. And hence, one of these bonds here have to break. And the one that is easily broken is this one here. So this bond will break, and then it will leave this position. So at the end of the day, you are going to form something like this, which is the final product of the Ester condensation reaction. I mean, the Claisen Ester condensation. So we have CH3, and then you have a double bond here, O, and then you have CH2, and then you can have this double bond what? O, and then OCH3. Plus, what do you think actually left? This one here, right? So this one, as it's leaving, is leaving with its own electron, which is own bond also. So that will form CH3O, the bond that left on top here as negative. So this is our alpha ketoester, okay? Alpha ketoester, and that is the product of the cleansing reaction, alpha ketoester. So you see how easy it is to navigate through, okay? See how easy it is to navigate through. So let's try another ester. This one that we tried was a little bit much easier. Let's try another ester if we can still follow the process. The most important thing is that you should know the process. Are you getting it? Now let's use this ester that we reacted here to see if we are going to get the final product at the end of the day. Okay, so this ester is ethyl etoxy or ethyl ethanoate. So erase our screen. Let's see ethyl ethanoate. The structure of ethyl ethanoate is CH3, CH2. We have it as CH3, CH2, C, double bond O, O, CH2, CH3. So we are reacting two molecules of this, right? Another one again. This is a bond here, okay? CH3, CH2, C, double bond O, O, CH2, CH3. Now, what do you think will be the product of this reaction? Now, the first step says a base removes a proton from an alpha carbon, creating an enolate. Now, the first thing is, let us pick this one and solve with this one first. So we say this is number 1. This is the first one we are working with. Then later we condense it with this one, which is the last one, the last ester. So working with that one first, let's pick it out. This CH3 and then CH2 and then C double bond O and then O CH2 CH3. Now the base that we are still going to use still remains etoxide, which can be written as OT minus. Now in some cases you can write it as OT minus, or you can write the full name, which is what? ETO minus, sorry, or you can write the full name, which is CH3 CH2O minus. So if we use this base now to react, which is I can decide to write it as O, reorient it, CH2 CH3. This is negative. Now the question is, which of them is the alpha carbon? Which here is the alpha carbon? Now you agree with me that this carbon here is carbonyl carbon, right? Now we say the carbon close to the carbonyl carbon is the alpha carbon. True or false? That is the alpha carbon. So in this case, what I'm going to do is this will be the alpha carbon. So the alpha hydrogen will be here, right? Now what I'm going to do now is, you know, we are abstracting a proton. Let me erase this from here first. This was initially CH2, right? Because we are removing a proton from here, we can easily bring that proton down here, because CH plus H will give us CH2, which was initially there. Then we'll now write the reagent that is abstracting the proton, which is negatively charged. Then at the end of the day, what do we say we do? This one will come here, abstract hydrogen, and then this one will kick into here to form a negative charge, which is the enolate. So the product of this reaction would be this. You have CH3, then you have CH, then the negative charge here, and then you have C double bond O, and then O CH2 CH3. Now in most cases, it's actually advisable to write these reactions in such a way, or these products in such a way, or let me say the intermediate, in such a way that they can easily react. Now this CH3 here will cause an hindrance, or a hindrance, if this compound wants to react. So the best way to do it is, we can decide to do it like this: CH, then here we can put the double bond here, which is the lone pair of electron. We can decide to put it here on top here, then let this CH3 be under here, so that it can easily react via this position. Then we can have our C double bond O, and then O CH2 CH3. Is that understood? So now, bringing that into the equation, what do you think will be the product of this reaction? Bringing that into this equation. So this is the enolate first. This is the enolate. Now we use this enolate to react with another ketone, which is the second ketone. So that is the second step. Use the enolate to react with the second ketone. So let me erase all. Now the second ketone, second ester, before I call ketone, second ester. Now the second ester is C double bond O. We have CH3 CH2, then we have O and CH2 CH3, plus the one we reacted was CH. We have negative charge here. I told you that this one has to come here, CH3, and then we have C double bond O, and then O CH2 CH3. Now how would the reaction go? This negative charge here will attack this bond here. Now, but before this negative charge attacks this carbon here, I told you that the orientation is in such a way that this one will be causing hindrance. So let's orient it in such a way that there wouldn't be any hindrance from that corner. Okay, so we can decide to put this one in a straight line, and then we can decide to put this like this, CH3, CH2, and then decide to put this like this, O, and then CH2, CH3. Okay, and then at the end of the day, what happened? This one cannot conveniently attack here, right? As it's attacking here, what will happen to this one? This one will pack up here. Okay, so the product of this reaction now will be equal to, these are very, very easy. Okay, so this will be equals to CH3, CH2, right? And then we'll have C. Now when that packs up, it becomes negative on top here, right? And then here it becomes what? O. Then we have CH2, CH3. Then we now have the let me say the linkage. Let me make it, the linkage is C. Here we have CH3, and then here we have C double bond O and O, CH2, CH3. So this is the product now. Now the final step is this enolate will come back to its initial position. So we come back to the last step. The product we've gotten now is CH3, CH2, C, O minus, O. Let me make it easier by saying this CH2, CH3. It's still the same thing. Then we'll have C, H. Then we'll have CH3 here. Then we'll have double bond O, O, CH2, CH3. Okay, now when this one kicks into this, supposed to use red pen to show arrow. Now when this kicks into this equation, it forms a double bond, right? Then this one here, we say when this one is kicking in, the valency of carbon will be more than 4. 1, 2, 3, 4, 5. And carbon ought to have a valency of how many? Of 4 only. 4 bonds around it for it to be complete octet. So in that case, as that one is actually kicking in, this other one, which is more labile, when we say more labile, it's more easier to remove, will kick out. And then the product of this reaction will be equal to, we are going to have CH3, CH2, and then C, double bond O, and then nothing will be here again. There you have CH, there here will be what? CH3, and then here will be what? C, double bond O, and then O, CH2, CH3. And this is the final product. Now, if you look at this product very well, you agree with me that it's synonymous to what we have here, right? CH3, CH2, CO, CH, then CH3, then CO, and then O, C. Okay, yes, it's supposed to be O, CH2, CH3. Yes, it's supposed to be O, CH2, CH3. There was an error here. Okay, so we are supposed to have here a CH2. Sorry about that. CH2, CH3. Okay, so that is the product of this reaction, and that is how to go about any reaction on Claisen Ester condensation reaction. So you see, it's pretty easy, right? So thank you for your time. Now you may want to practice more following the same procedure. The most important thing here in most organic reaction mechanism is know which is attacking which and where to remove. We said the base removes a proton from an alpha carbon. Everyone knows what that is now. This is the alpha carbon. This is the alpha proton, right? The hydrogen. This base comes here, remove it to form the product of this base supposed to be here, which is when this one reacts, we said it will form ethanol, right? CH3, CH2, and then what? OH. Okay, so that is practically all. And then this one kicks in to form the enolate ion. The enolate ion will attack this other one here Please paying attention to the orientation in such a way that it can easily react. So when this one came in attack here, this one comes up to form minus. Now they are now joined together. This one kicks in, this one goes out, and then the final product is formed. Thank you for your time. Okay.